Okay, so this video we're going to look at the Laplace transformation of a constant. And in this case, our constant will be k, where k is any integer, so it could be any value. Now, what I'm going to do is I'm going to show you how to derive the Laplace transformation of that constant. That's what this video is going to be all about. So Laplace transformation, now that's used to try and simplify functions, try and make it easier to find the solutions. So it can be used in differential equations, in statistics and in physics. So Laplace transformation, what is that? Well, let's start off with the terminology. So the Laplace transformation, so it's this kind of fancy L, and it's of whatever this f of t is. So our input is going to be this here, which is our constant k. So that's what we're going to put in there. And then what it equals is the limit as a approaches infinity. So I'm going to use a as my variable for that. And it's the integral from 0 to a. Now, just to jump in here why I've got a 0 here, because this is the unilateral version of the Laplace transformation. Now, if I wanted the bilateral version, I'd go from negative infinity to this a. So anyway, continuing on with what's in the integrand. So now, standard in all Laplace transformation, inside the integrand I put e to the power of minus st, e the exponential function. And s here, that's my parameter. So s is the parameter. So that's my variable there. And t is most commonly a function of time. So that's the value of time. So t, let's put my arrows there, that is time. Now it doesn't have to be time, it can just be a variable, for example, in some other equations like in statistics or stuff like that. But here, I'm going to say that it's time, but it can be anything. And then with that, inside this integrand, I integrate with f of t with respect to t. Okay, so that's the general way of finding the Laplace transformation. Okay, so now the Laplace transformation of our constant. So now I could change this terminology and put stuff in there that we already know. So limit as a approaches infinity, 0 to a. I've got e to the minus st, that's going to stay, and dt. And my f of t is just k. So k is just my variable for a constant. Okay, so now we're ready to integrate. So this here, integral that we can handle pretty reasonably well. So we'll let u equal minus st, du equal minus s, and that's obviously with respect to t, and dt, and get dt on its own. So then I get du over s and a minus in there. Okay, now my parameters of integration, I'm just going to leave them as they are because I'm going to go back into the t at the end. So now I've got the limit as a approaches infinity. My integral now in the u world is 0 to a, k, e to the u, du, and then I need a minus and an s. So minus I'm going to bring to here, and the s I'm just going to divide my integrand by it. Okay, so now we're ready to integrate. So now I've got the limit as a approaches infinity. Now integrating this straight off, my k over s will stay because I'm integrating with respect to u. So I just put this in brackets, so minus k over s. And e to the u, well, u is minus st, so I can plug that back in. So e to the minus st. So that takes care of all of that. Everything else stays as it is. And then my parameters of integration, 0 to a, I can just put there like that. Okay, now just a word here, we just need to work out what our values of s could possibly be. So first of all, if s is 0, then this becomes undefined and our limit will approach infinity. So we'll say that s will not equal 0. So what about less than 0? Well, if s is less than 0, for example here my integrand here is a negative number, as my a approaches infinity, this integral here also approaches infinity. So it's also good to point out that s must be larger than 0. So if I just put that and also add to that, it cannot be less than 0, then we're clear on where my s will be. Okay, so now let's finish off the integration and find the limit. So the limit as a approaches infinity. So let's take the values of a and 0 for my t, because that's what I'm integrating with respect to. So minus k over s, that's just going to stay. I'll leave that on the outside. Then I'll do e to the minus st for each of these variables. So if it's a, I've got e to the minus as. So that's that one. And if t is 0, this just becomes 1. So that's then just minus 1. Okay, so let's clear this off, bring it up to the top. Okay, let's just tidy this up a little bit and get rid of these brackets. So I've got a minus value here and a minus value here. So I might just bring them to the front of our limit. So the limit as a approaches infinity. So minus ks times minus 1, that's just going to give me k over s. And then minus k over s times e to the minus as. That then becomes minus k e to the minus as over s. Okay, so I need to take the limit of this. So I'll leave that all in the bracket so it's in the limit. So the notation is good. Okay, so what happens as a approaches infinity? Well, it's not going to affect the first term. So I'm now left with k over s. That's fine. Now what happens here if this approaches infinity? So I've got negative infinity times s. So the limit of that one is going to approach 0. So therefore I'm going to be subtracting 0. So that is my final answer for my limit as a approaches infinity. So therefore we've just shown that the Laplace transform of k as a approaches infinity of 0 to a of all of this, that simplifies down to k over s. Now as we did the definite integral, there's no need for a plus c or anything like that. So that's our answer. Now to write this in correct Laplace notation, I'm going to now go, so my Laplace sign, so my fancy L of k, because that's what I wanted to find my Laplace transformation, that equals k over s. Now, a couple of examples here. Let's say, for example, if k was 1, I would then have my Laplace transform of 1, that equals 1 over s. And then for another example, if my k was, for example, pi, so the Laplace transform of pi, that would equal pi over s. So that's standard Laplace transformation for a constant, and we've derived how to get it, and that will be our final answer, which can be used for any value of k as long as k is an integer. Okay, so next video we're going to look into polynomials and do the Laplace transformation of a polynomial, and then after that we're going to try some trigonometric functions and some logarithmic functions. Okay, so keep an eye on the link below to see when those videos are going to be available. Okay, so here's my answer to what we got so far. Okay.